Mhm. What does that mean? Tell me what filtration is without using the word filtration or filtering. Okay. Okay. So in the kidney, right? What is the kidney filtering? Let's start with that. What will the kidney filter? What is the kidney filtering? It's filtering blood. That is right, isn't it? Yeah, it's filtering blood. Which part of blood is this filtering? Which components of blood is being filtered? The plasma, correct? Blood has how many components? We can say cellular components and what? Water. Good. So which parts will I filter normally? A normal kidney should filter the plasma, not the cells. We're filtering the water part of blood. Excellent. Okay. Now, what is plasma made up of? Water and what? What else does plasma contain besides water? Plasma, no, cells different. Plasma itself contains what? Besides water, what else does it contain? Exactly. So plasma has water, but it also has what? Proteins. Albumin. It's gonna, let's say it's gonna have soluble molecules and what? Insoluble molecules. Molecules that actually dissolve in water. Dissolved gases, oxygen, CO2. Dissolved molecules like glucose, etc. Then it has dissolved molecules like maybe also electrolytes, sodium, phosphate, right? Chloride, calcium, etc. They are water soluble. It's going to have the insoluble molecules like proteins, immunoglobulins, albumin. They're all in plasma. Coagulation factors, proteins. Awesome. Okay. So when the so what do we filter stuff? Glomerulus, right? What makes the glomerulus a good medium for filtration? What is the structure of the glomerulus? So literally, let's assuming filtration is what I want to get something through something, right? So I want to something to pass through a medium, right, to the other side. Like just layman word, we can say that's what filtration means. Get something through a medium, right, to the other side. And then you see what remains. Whatever remains is what called the word ultrafiltrate, correct? Yeah. So the medium in this case is what is the glomerulus. That's what I want to get it through. Glomerulus has layers. So it has the blood vessels that will bring blood in or plasma in. Then blood vessels have their own basement membrane. They have their own endothelial layer, basement membrane. And then we have the other side where we have the Bowman's space, where we're going to filtrate, the ultrafiltrate will be. Also has its own cells, epithelial lining and basement membrane. So the membrane has to be what? Permeable, right? For me to get something through, it cannot be rock solid. It has to be permeable. So the membrane is what? It's what do we call the basement membrane that has? It's discontinuous, like it has holes in it. Right. Thank you very much. Good. Then, so it's gonna have that. Even the endothelial cells too, there are spaces between them. Spaces between endothelial cells. On the epithelial underside, there are also gonna be spaces fenestrated so that things can go through. But it's gonna limit the size, right, of things that go through. Makes sense. What will make end up on the other side depends on things that can only go through. So the size of the fenestrator will determine the content of the ultrafiltrate on the other side. All right. Then another thing that the membrane has is what? We also have a charge now. So not only are we filtering by size, we're filtering by charge, right? And the major charge on the membrane is what? Is negative, which means it will naturally repel what? Same charge or like charges, negative charge molecules, like they happen. Good. So, what we get to the other side, remember, of course, the objective, the main objective for filtration is we want to get toxins out, waste products. We want to get them out of the plasma and keep the things we want. But unfortunately, when you filter, right, initially that filtration band does not, it is not too efficient. It's going to filter both waste product as well as some things that are what that we need that are not waste product. So it's filtering water and everything that is dissolved in water. It's going to filter glucose, amino acid, electrolyte, etc. together with water dissolved there. It can filter some but it's gonna filter then creatinine dissolved in water also BUN, right? Those are waste products. We actually want them out, but we're gonna also filter some things that we that are not waste products. Good. But ideally, protein should not. Large proteins should not be filtered. Immunoglobulins, no. Those will be limited by either size or by charge. Okay. So we have the barrier to filter. Next thing is we need to create what? Force, right? To filter. Yeah, I just don't need a barrier. I need to be able to push those things through. Create a force or a pressure that will drive those things through the barrier. That's why we now have what? Our filtration pressure. Right. And then filtration pressure will be determined by what? By the Stirling forces, which includes hydrostatic pressure and oncotic pressure. So we want the hydrostatic pressure and to be high on the glomerular side than the Bowman space. We want the oncotic pressure in the Bowman space to be higher than the glomerular side. We want the oncotic pressure on the glomerular side to be lower than the Bowman space, right? So basically, hydrostatic pressure will push, create a positive pressure for filtration, while oncotic pressure opposes filtration in the glomerular side. Yeah. So, and once you have those pressure, you also need to be able to regulate them. You need to be able to adjust the filtration pressure. Either we push, create more pressure to filter more, or create less pressure to filter less, depending on the state of the body. And that's why you have your efferent and your afferent arteriole, which are highly regulated. So since hydrostatic pressure is the major player in determining the pressure, I can regulate how much blood comes in and how much blood is leaving, and regulate the pressure there. So the system is right, everything is in place for better regulation, right, of filtration. So let's say we finally get the ultrafiltrate into the Bowman space. Remember, this ultrafiltrate contains what? Both waste products and non-waste, right? Materials. So what do we do next? We now need to find a way to get what? The non-waste back into the blood. Right. And that's why we now have what? Reabsorption. Very good. We need to get them back somehow. Reabsorption. And then sometimes too, there will be some waste products that will not be completely filtered. Make sense? So we also need a way to make sure those ones that are not filtered, we need to figure out a way to still get them into the what? Into the urine anyway. And that's why we now have what? Secretion. Right. Right, from the plasma back into the tubule. Right. So compared to filtration, although filtration and secretion, they both get the content from the plasma, right, into the tubule. Filtration is what? Largely a passive process. It is driven by static pressure. It's largely passive. It doesn't require any active input of ATP. We don't have transporters in the membrane actively pumping anything. But secretion, on the other hand, will now use what? Is an active process. It requires pumps, transporters. You take the molecule from that have molecules that escaped filtration to actively pump them right from the plasma into from the basolateral membrane of the tubules into the through the apical membrane into the what? Lumen of the tubules. While reabsorption will take the molecule from the lumen of the tubule using apical transporters, get them back into the what? Into the plasma or the basolateral side. Yeah. So those processes require energy to do that now. They require some energy, either active or passive. Right. So that's why our tubules have transporters now, right? Depending on what you want to get in or out. All those are vital non-waste, right? So they are glucose, sodium, the electrolytes, the amino acid, they have what? Transporters to get them reabsorbed. And then also BUN can be secreted for those that BUN that escaped filtration can be actively secreted, yeah, into the tubule. So when all these three processes takes place, we filter what we can, we reabsorb what we still need, we secrete some additional waste products. Now whatever now remains in the tubule will now be what? Excreted. So which means those three processes play a major role in what? In final urine formation. Right. That's how the kidneys form urine. Because urine is whatever remains that is excreted out of the body. How do we form the urine content? Filtration will contribute, secretion will contribute, and then reabsorption will remove from it. And then whatever remains is urine. Right. That's urine. Right. Awesome. Right. So if I want to know, oh right, how much of a molecule is excreted out of the body, or excretion rate of a molecule, right? All I need to know is how does the kidney handle that molecule? Does the kidney filter that molecule? Does it reabsorb it? Does it secrete it? So right, for me to know how much is excreted. So if it's a molecule that is both filtered and reabsorbed, then I need to find the amount filtered, subtract it from the amount reabsorbed. That will tell me the amount that will remain, right? That excreted. If the molecule is filtered, reabsorbed and secreted, all three, then filtered amount plus secreted amount minus reabsorbed amount will tell me the amount that will remain in the urine that will be secreted. If the molecule is only secreted, I just need to know the secreted amount. That will be equals to the excreted amount. Yeah. So that's how you know, okay, how much of the molecule will be in the urine by the way the kidney handle the molecule. So if I now say, let's extrapolate from that. Which molecules will be best to estimate GFR? So I want to know at what rate does the kidney filter plasma. I need to find a molecule that is what mostly filtered with little or no reabsorption, right? Or secretion. That would be the best estimate of GFR, because I know that whatever the molecule, whatever the rate of excretion the molecule E is undergoing, that will be equal to what? The amount that is filtered, because it's not handled any other way except filtration only, right? And that's why molecules like although creatine is not only filtered, it's actually also secreted a little bit, but mostly filtered. It can be a good measure, at least of an endogenous molecule, right, for estimating GFR. Then inulin will be a perfect one. Inulin is only filtered. It is not neither secreted nor reabsorbed. So it's equal to GFR, right? It's only filtered. If I want to determine a molecule, if I want to determine the reabsorption rate, then I will look for a molecule that is completely reabsorbed, like glucose, amino acid. They are completely reabsorbed. They shouldn't appear in urine at all, in normal kidney, or in healthy people. Completely reabsorbed. They're going to be a good way to estimate reabsorption rate of the kidneys. If I want to estimate the total blood flow, since we know that filtration is removing part of the plasma, we're filtering the plasma, and then when I get to secretion too, I'm also removing from the plasma, which means both those two things are going to be a good estimate of what the total amount of blood that is flowing through, right, the whole kidney. And that's why molecules that are both filtered and secreted completely would be a good, right, measure of total blood flow or plasma flow to the kidneys, because I'm removing in both their situation. So if I can find the amount that is filtered plus the amount that is secreted from the blood, I can estimate the volume that flow through. Yeah, because concentration is what? Is amount over volume. So if I know concentration of the drug, I know the amount, I can estimate the volume of blood that flow through. So that's why molecules that are both filtered and secreted, like para-aminoipric acid, right, will be a good estimate of renal plasma flow. So renal handling is super, super important. And you gotta know how the kidney handle high yield molecules. You gotta know how the kidney handle glucose, sodium, chloride, phosphate, calcium, magnesium, amino acids. You gotta know them. You gotta know the normal water, right? Water too. You gotta know the normal so that when it's a disease state, you can quickly predict what the problem is. Yeah. Imagine if I'm seeing glucose in the urine. I don't need anybody to tell me, right? Is either somebody has too much glucose, they are filtering too much, or there's something wrong where glucose is reabsorbed, which is the PCT. I'm seeing too much magnesium in the urine. It's going to be the thick acidic limb of Henle. That's where magnesium is mostly reabsorbed, right? I'm seeing too much phosphate in the urine. I know it's the PCT. I'm seeing amino acid in the urine, PCT, right? The urine is too dilute. All right, I know collecting tube likely. So the problem is that's why most of the water is reabsorbed in response to ADH, right? So that is how we master renal. Good. Medications to diuretics, right? Yeah, gotta know them. Know what transporter. Know where they work in the renal tubules, things like that. Know the consequences. Yeah, know common side effects in terms of renal pharmacology, right? Yeah, so those we should know too. Anything else on renal that you read? Mm-hmm. Mm-hmm. Yes. Mhm. Right. So you want to know, okay, good. How the kidneys handle water with or without ADH? Which parts will be dilute concentrates, right? Right. Like you said, that's pretty good. That's we're gonna know in the PCT, the concentration of urine is the same as plasma, right? Because at that point you have what isosmotic, right? Water reabsorption. So it can be the same concentration. And like you said, we get to the descending limb of the loop of NH, right? The thin descending limb that is permeable to water only, but not solute. So the urine becomes diluted, sorry, concentrated. As it goes down, the thick, thin descending limb becomes diluted all the way, concentrated rather, all the way to the tip of the loop of ND, which is gonna be the most concentrated in the absence of ADH. Yeah. But then as it ascends, now we get to the thick ascending limb of Henle, which is permeable to solute, but not water. So sodium, chloride, potassium, right, magnesium, which is will be reabsorbed there. Then that's we call that the diluting segment of the kidney. Diluting segment of the kidneys. And then BCT2, more sodium chloride reabsorption than water, becomes more diluted. And then correcting tubule, yeah, in terms of ADH, should become very, very concentrated now. Yeah. If there's no ADH, it's gonna be very, very dilute. Yeah, so super important. Right, and don't forget ADH has at least three functions in the kidneys. Activate aquaporin, right? That's one. And just aqua, and sometimes it can be a little bit coy. Aquaporins themselves, they're like in the membrane. Know how insulin works, where insulin binds to the receptor on the muscle and adipose tissue, right, and actually phosphorylates the GLUT4 transporters in the cytoplasm, and they will now go and be embedded right on the membrane. Same thing with ADH. ADH, the aquaporins are actually what in the cytoplasm, right? And then ADH once it stimulates V1 receptor, which is GS, so then phosphorylate, right? Those transporters in cytoplasm, and then they become embedded on the membrane of the principal cells, and that will make the membrane permeable, right? And water will be reabsorbed. But they also activate what UT1 receptor channels, urea transporters, which will increase urea reabsorption. And then it also works at what thick ascending limb of Henle, right? Activates sodium chloride potassium cotransporter. So the essence for urea and sodium chloride cotransporter as well is to create what high interstitial, right? Concentration. so that water can move out easily. We call that counter current multiplication, right? Right. Counter current is basically just a way to create like a osmotic gradient in the interstitium of the kidneys, in the usually in the medulla, and water will be driven out of the lumen, right, into the interstitium and then into the basa rectal blood vessels. Yeah. So at least three functions, which explains why. So based on those three mechanisms, how can you treat SIDH? Right, we have three mechanisms of ADH at least, right? So that gives me at least two mechanisms of treatment or two principles of management. So what can we do? Based in patient with SIDH, what can I do to treat SIDH? Patient has SIDH, they are drawing too much water. Isn't that what SIDH would do? How can you do that? You can block ADH receptor itself, right? We have ADH receptor blockers. All right, what else can I do? And you block ADH receptor, that would do that. Can I block sodium chloride cotransporter, potassium cotransporter? What? How would I block that? Sodium chloride potassium cotransporter is thick ascending lipid for NLU. How will I block that? Loop diuretics. Yes, right. So how do you treat SIDH? You're blocking either EDH receptor itself or I'm blocking the sodium chloride potassium cotransporter. Loop diuretics. That's what you do. So how do you treat DI? Diuresis insipidus. For which what type? Yeah. So how would that help? If I block sodium chloride cotransferase in the DCT, what will be activated? What will be activated with RAAS? That's why it's a diuretic, right? So it blocks sodium chloride. So first of all, what's the problem in nephrogenic DI or in DI? The problem in DI is they are losing its water has been lost, not solutes. correct? It's actually water, free water. That's always being lost. So urine is dilute, very, very dilute. If I block a solute transporter now, sodium chloride, what happens to the urine? Urine becomes more concentrated, which means less water, more solute is in there. So that already is saving water already in the first place. They are losing less dilute urine. That's one plus with that. The second plus is the diuresis will lead to what? RAAS activation. What will angiotensin 2 do? And aldosterone. So aldosterone increase sodium reduction way in the collecting tool, and then what will 82 do? 82 also stimulates sodium reduction way in the PCT. If sodium is being reduced, what will follow sodium? Water. So there's less, right? Less urine volume. Yeah, less urine volume. So that's why thiazide is beneficial in NDI, diabetes insipidus, nephrogenic DI. Yeah. Mm-hmm. And if sodium is reabsorbed, water will follow, right? Yeah. So the urine that's been lost eventually becomes less watery. Can become, right? It's gonna be, volume decreases, water in there decreases, right? That helps those patients. Excellent. The kidney is your best friend. Without the kidneys, I wonder what the heart and the brain will do anyway. But they won't survive.